Hello students, good day. I hope all of you are well. From today, we will start a new section of synchronization where multiple processes or multiple threads they compete for resources in a system. We may call that system as a multi-programming environment or a multi-processing environment. However, any system where we have a contention among multiple processes or threads, uh, or in such systems we require synchronization mechanisms. Synchronization means that if we have multiple processes or threads running in the same system, then they may compete for several resources at the same time. In order to make sure that this competition among multiple threads or processes may not lead to uh, wrong execution of a process or wrong results produced by a process, we want to have some mechanisms that ensure that processes they do not interfere with each other or do not interfere with the resources that are occupied or requested by other processes in the same system. First of all, we will have a look why these problems are arised in a system. Then we will see what are their possible solutions, and then we will try to comprehend the whole situation by looking towards multiple possibilities or multiple techniques through which we may avoid to have this problem altogether. So this in this section we will talk about threads, we will talk about multi-threaded models, and then we will see how the execution of a process having multiple threads or in a multi-processing environment, how we may have multiple processes uh, running in working together, how they uh, compete with the resources, and how we may have mechanisms to avoid such conflicts. So the first thing that we may encounter in this discussion is the concept of thread. Thread, as we had discussed a couple of chapters earlier, is a unit of execution. So it is possible that we have a process having multiple threads running in parallel in a system. If we have a client server application where the server is responsible for performing multiple jobs, it is possible that that server is waiting for the users to request some particular resource. Then the server is also responsible for establishing a connection between the client and itself. Then maybe the same server is also responsible for fetching the resources from the hard disks, and then there are multiple other concurrency synchronization issues that are running within this server. There are multiple layers on which the server has to operate. In such scenario, if we have a single threaded environment where we have let's suppose multiple processes responsible for each of these tasks, it is possible that then we have to define the mechanism that is there to enhance the communication among multiple processes that are performing these related jobs. However, when we make them different processes, then the operating system has to intervene every time, which means that these processes, there is a possibility that these processes may get different time slots and different efficiencies, or so different performance measures will be considered against each of these processes, which means that the efficiency of the whole system may compromise overall. So to resolve it, we usually have one process and we have multiple threads that are associated with this particular process. In such scenario, these threads of the same process, they communicate with each other, and the operating system is not responsible for handling the scheduling of these threads within this same process. So it is possible that in one case there are more requests at the server than it can process. So in this way, we may have better load balancing mechanisms compared to if we are dealing with different processes. So threads are quite important because multiple locations of a process may be able to execute simultaneously if we have multiple processors that are present on a server, and then we can have their control differently, and we can easily associate one thread to one type of job. And overall in the process we may able to balance the load and synchronization among these threads on without having any dependency on any operating system or other external factors. Along with the advantages that we have discussed so far, including the single administrative control over the execution of a process, as well as distributed execution of multiple threads in the same process, we have several advantages that are reflected on the user side. Uh, these advantages include the response that a usual user expects from the system, as well as from the developer side or the administrator of the server. From their side, they have several advantages in the implementation as well. So the first among this list is the responsiveness. Responsiveness means that if we have multiple threads of the same process, and one thread goes for the IO, or just like the example we had earlier in the server, if one thread is associated with receiving the user's requests, so other processes can carry on their execution at the same time. So if part of the process is blocked for some reason, including some IO operation, still other threads can continue with their execution simultaneously. So a process, or part of the process is in the blocked state, and part of the process is in the running state simultaneously at the same time. So now you can see that you may have added advantage over a single process, as if a process is blocked, the whole thing is blocked. You cannot execute this process anymore. However, if you have a multi-threaded application, over there you may have some thread that is blocked for some IO, but the time or the scheduling of that process may not get affected because of other IO operations or interaction with the devices that this process is experiencing at the same time. This affects the efficient execution of a process, as well as the user gets better response from the system, because the thread that is blocked will not affect the scheduling of the whole process. So by this process, the user will still get some response. The other advantage that the user may feel is the resource sharing. As threads share some resources, uh, that is not the case with the usual process environment. So we have easier mechanisms to have message passing and sharing of resources among threads compared to processes. The third advantage is the economy of scale. Threads, as we do not require to create new copies of code or data. Creation of a thread is a lot cheaper compared to the creation of a whole new process. Also, as the switching among the threads do not require uh, much much data to be saved and reload onto the processor. It means that the context switching or the thread switching will be a lot more efficient compared to the switching among multiple processes. Another advantage that we get through threads is the scalability. As we have multiple processors now in almost every system, and in huge servers we have this parallel environment where we have multiple processors working in parallel. If we have multiple threads, so they can take advantage of these multiple processes where multiple threads can execute simultaneously in a multiprocessor architecture. However, if we have processors, we may have to devise new mechanisms that can be supported by the operating system in order to get full advantage from different types of such architectures. This is a pictorial representation of threads. So you can see we are up till now only familiar with this type of processes, and each process has a code, some data, and some files associated with it. While there are some registers and the stack pointer, I hope you know that stack pointer is a quite important pointer that is used to store the return address of the calling function. This is quite important if you have multiple functions and you want to store the return address from where you can continue the execution. So this is an overview of a process that is single threaded. However, if we have a multi-threaded process, the code, data and files, they remain the same, while the register and stack, they are independent for each of the each of the thread. So you can see that each thread has its own set of registers as well as stack. So they are a complete set of execution in them. So you can see that a thread can call functions, it can return from them, it can store values in registers, and so a thread is quite useful when we are implementing applications which are which are performing multiple tasks simultaneously. So we can assign multiple threads to multiple section of code or multiple tasks. To signify the concept of threads, over here we have listed several differences between processes and threads. The first one is the processes are resource intensive, so they are heavyweight. On the other hand, threads are lightweight and require quite less number of resources compared to a process. If you want to create a new thread in a process, you require quite a few resources compared to creation of a new child process. The other difference between processes and threads is that switching among multiple processes requires intervention from the operating system. So operating system handles the switching among multiple processes. However, the switching among multiple threads of the same process does not require any intervention or any assistance from the operating system side. The third difference between processes and threads is that when we have multi-processing environment, over there each process has its own memory, all the files and everything associated with it in independent manner. While on the other hand, all threads of a same process, they can share all the resources from that process. So they can share all the files, all the child processes, so everything they can share among each other. Another difference between processes and threads is if one process is blocked for some IO operation, the execution is not possible for this particular process. So the CPU has to schedule some other process even within the allocated time of this process. However, this problem can be solved quite efficiently with the help of threads, where if one thread is blocked and it is waiting for some IO to complete, a second thread can take its time slot, so which does not affect the efficiency of the process altogether. In terms of processes, another difference is that every process in a system is independent of each other, so they do not interfere. Usually it's one of the responsibility of operating system to ensure that multiple processes, they do not interfere with each other, unless we have some legitimate mechanism. On the other hand, we have in threads, one thread can communicate with the other with a lot of easier mechanisms that are available. So one thread can read, write, or access the data of the other thread quite easily. The differences that we had on the previous slide reflect one interesting characteristic of threads, and probably that is one of the reasons why threads are so popular, is that in a multi-threaded environment, if we have some IO extensive application, we can associate some thread with it. So if that thread is blocked for the IO request or IO operation, the other can continue their execution, which means that the process will still in the execution state or in the running state while it is also waiting for some IO. So it improves the overall efficiency of a process. The switching among multiple threads, as we had earlier discussed, that context switching is quite a resource consuming operation. So if we do not require to save the whole set of data and files and everything, then definitely that switching can take place at a faster rate. So when we have threads, we have, because we have less amount of data and we have only a few things that we want to save and reload, so this switching among multiple threads of the same process, it is a lot faster compared to switching among processes. These are the reasons why a thread is termed as a lightweight process. However, there are some things that we should keep in mind, that even though we have multiple threads of the same process, at one point in time, only one thread can be in the execution in one CPU or in one processor. So if we have a single processor system, at any point in time there can be only one thread that is in the running state, and other threads, they can be in ready state or waiting state, or all the states are possible as we had for processes. Threads have different stacks and registers, and they allow them to operate in independent manner. So by having different stack pointers, they can keep track of the calling functions and the return values, and a sequence, an autonomous sequence on their own, as well as they have a set of registers. They can store values and they can perform actual operations. So that is why threads provides us a mix of autonomous as well as some independence among multiple threads, as they are sharing multiple stuff with each other. So there are a lot of positive traits or positive characteristics that are associated with threads, and that is why now we are moving more towards multi-threaded applications. When we have multi-threaded applications, we have several issues that we have to face, and various challenges that we have to answer uh, before we can have a successful system. You can see that if we have multi-threaded applications, we can have multiple threads running on the same code, which can cause quite some synchronization problems. And we'll talk about one of them just in a couple of minutes. Then to complicate the scenario, now we have multi-processor systems where along with having multiple threads, we have multiple processors. So now you can see that the whole scenario becomes a lot more complicated. But having both of these things, multi-thread applications as well as multi-processor systems, now it is possible that we may have concurrent processing of one process. So now it is possible that multiple threads of the same process, they can run simultaneously exact at the same time in different CPUs. So and that raises a lot of other challenges that we were not aware before. So now we have different interesting problems and their solutions uh, are provided every now and then. One of the problems, and very interesting problem, that is associated with this synchronization thing is critical section. So here we have an example of a critical section. As you can see that over here we have one variable that is being incremented, and before this increment and just after this increment we have its values printed out. And then the very same variable is in a multiplication operation, and again before the multiplication operation we have its value printed out as well as after the multiplication operation. So you can see that this should not be a problem for a single threaded application. However, now let's assume that we have multiple threads running in parallel onto multiprocessor or multiprocessing environment where we have multiple threads as well as we have multiple processors present in the system. So you can see that it is possible that one thread may start its execution from here. Simultaneously, another thread starts its execution from here. So the one thread is here and it just increments the value, and then it stops over here for some reason, and then the next one moves along onto the next processor. So it prints out the value, it adds it, then prints the value one more time, then prints the value before the multiplication, does this operation, and then prints the value one more time, and probably exits. In the meanwhile, the first thread now prints the value after the increment. So you can see the discrepancy over here that is going to rise, that before the increment the value may be like 1, but after the increment the value will be a 1 increment as well as a multiplication, the result of a multiplication operation as well. So you can see that over here we will have a quite an entirely different value that should not be expected in the usual execution of this program. So you can see that we have different output just based on the arbitrary running of the threads. So this problem is termed as critical section problem. Now, in order to enhance our understanding about how a process having multiple threads operate in a real world scenario, let's have a discussion about some models that are present for multi-threading. As you are aware that we have a hardware, a machine, and on top of that hardware we have an intermediate layer that we term as the operating system, and on top of that operating system we usually have user processes. So now let's assume that we have a very good hardware that support multi-processing, uh, and having pipelines and architecture that where efficient execution of multiple threads is possible. At the same time, we have a user application that may try to utilize all of the features of that particular hardware in the best possible way. So the application has all the mechanisms to exploit or to enhance the efficiency of its or the performance of this application by utilizing the features of the uh, hardware. However, uh, between these two uh, layers, we have an operating system. And now assume that the operating system does not support multi-threading altogether. So in such situations, you can assume, you can visualize probably that the process may not get all the advantages that are being coded in it, as well as the advantages that it can extract from the hardware, because the operating system that is uh, providing facility to the process to get the benefit of the hardware, it is not supportive enough to let the process utilize the hardware in an efficient way. So the operating system performs this or facilitate this interaction between the process and the hardware. So there are multiple models that are present that allows us to allow us to have an interaction between the user level process as well as the operating system level components. So here we have some threads that are present at the user side, at the application of the user level, as well as on the operating system side that we call as the kernel threads. The user level threads, they are usually managed by the developers, and there are several libraries that are present at the user side through which they can enhance the working of their applications, to work in a better way on a multi processing environment. These libraries include POSIX, pthreads, Windows threads, Java threads. So these libraries are present where the developers can utilize them to have a better efficiency of their own applications. However, to utilize the hardware in the best possible manner, we have some threads at the operating system level, the kernel threads. The kernel threads, they are supported by the kernel, and they provide a mapping to the user level threads through which they can utilize the features of the machine, the hardware. So there are several kernel level threads that are present in multiple operating systems. The models that we will have a look today are many to one model, one to one model, and many to many model. Just having an overview, many to one means that there are many threads, multiple threads at the user level, and there is only one thread at the kernel level. Then we have one to one mapping, which means that one thread of the user or user application level is having a mapping on one thread at the operating system level. And then we have many to many mapping, which means that multiple threads at the user level are mapped onto multiple threads onto the kernel level or the operating system level. And we will have just a look over all these three models of multi-threading. The first one is many-to-one, which means that multiple threads at the user level, they are mapped onto a single thread at the kernel level, which means that if multiple threads are uh, working at different pace and different components in the user application, all of them they are mapped to a single thread of execution on the kernel level. And probably now you can map this model onto the example that we were having just a while ago, that an application that is there to utilize multiple features of multi-threading is restricted by a single thread at the kernel level. So you can see that even having multiple threads at the user level, whenever you have some IO operation or you have something that blocks the execution of a thread, so the whole process will appear to be blocked at the user side, which means that the kernel level thread is occupied to do some task, which means that other threads of the same application are not able to utilize all the features of multi-threading environment. All the whole process will become blocked, and the operating system will schedule some other process, which means that uh, even having multiple threads at the application level, still the whole application will appear as an enhancement of single threaded application, because in actual it will execute in the system at a single thread level. Maybe those threads are different with the user level application. However, at the level of their execution, it will appear, or it will give the efficiency of similar to a process that has single thread of execution. As you may have already concluded that a one-to-many model may not be that efficient, so it's not in use anymore, and very few systems today may use such model. The next model is one-to-one, where one thread at the user level is mapped onto one thread at the kernel level. So you can see that the efficiency of such a system overall will be a lot more compared to the efficiency of a system where we have only a single thread at the kernel level. So whatever the application layer or the user application demands from the operating system to give support for multi-threading environment, the operating system kernel is there to help such situations. However, we have once we have such scenario, the cost of the operating system and the overall cost of the running the multiple processes, it may increase such that we may have to restrict to the number of concurrent threads at the kernel level that are associated with one application. However, as you can see that from the developer's perspective, it's almost ultimate freedom to them that as many threads they want to associate with their application, they will get the support from the operating system. And now, if the hardware supports the multi-threading architecture, the application can extract and exploit all the features that are provided by the hardware and being developed by the developer. However, as I had mentioned earlier, that this model may produce some overhead on the operating system side. So we again have some restrictions on this model, because this is probably an ideal case, but the resources are not unlimited. So we have to restrict on some levels, just to ensure that the resources of the operating system, they are not just consumed by a couple of processes. Moving on, we have the many-to-many model. As you have guessed from or discussion from the two earlier models, uh, many to one as well as one to one, that both of them are not very practical in the current environment, as well as with the number of resources that are consumed by one application. So we have another model that is many to many, where multiple threads at the user level, they are mapped to multiple threads at the kernel level. So the operating system generates a particular number of threads for any particular application that requires multiple threads, and it associates these threads with to that application. And now multiple threads at the user application level layer, they can be mapped onto multiple threads on the kernel level. However, this mapping is not static, rather dynamic, in a way that one thread, one kernel level thread that is associated with one user level thread may change this mapping during the execution of the program. So these are the three models of multi-threading systems that we have discussed today, along with the basic description about threads, as well as advantages and some synchronization issues that may arise in such environments. Uh, so that is all for today, students. Thank you.